Okay, go ahead.
Oh, there we go. Is everyone in?
Just your presence.
Yes,
Oh, there you go.
my name is
All right. Fantastic.
Sarah Help. Okay, welcome everybody to HO Colloquium. Today's speaker is Rahul Sharma. Rahul Sharma is a postdoctoral research fellow at the Northumbria University in the United Kingdom. He received his doctoral degree from the University of Sheffield in 2018, then worked as a postdoc at the University of Alcalá in Spain. His research interests are mainly focused on the observational aspects of MHD waves in the solar atmosphere. Today he will be speaking on diagnostics of turbulent corona using transverse Alfvénic waves. Rahul.
Thank you, Marshmi. So I hope I'm audible to everyone online. So thank you so much for the opportunity, and thank you everyone for joining in. So today in my talk, I will be talking basically about some of the characteristics of the transverse Alfvénic waves, and also for some of the recent work that we have been doing in some recent times with Richard Morton and other people as well. So in my talk today, I will be giving a very brief, and when I say brief, it's really brief, overview of how exactly these transverse magnetic waves, I will come down to the Alfvénic nominations as well. And then I'm going to talk a bit more about the seismological applications of these waves and how these can be used to diagnose some of the parameters, let's say the density and the magnetic field. Then I'm going to talk more in detail about the transverse energy injection scales or the perpendicular correlation length that we managed to estimate using these waves. And in the end, I will briefly touch upon the role of inhomogeneity in the solar atmosphere and how this can actually affect the characteristics of these waves as we kind of observe them and diagnose them so far. So starting with the wave heating kind of the idea. So generally it's kind of most people know about, like, there's the thermal heating problem where the temperature in above the transition region rises kind of very abruptly, and we don't know what are the responsible mechanisms for that kind of behavior. So one of the views is regarding this wave-based heating. So a very common ingredient for wave heating models is that the convective motions down in the photosphere, they kind of perturb the magnetic fields, and these waves or these transverse perturbation do propagate along the magnetic field, and they process through different layers of the solar atmosphere and eventually dissipate in heating the solar atmosphere as well as powering the solar wind as well. So here is a very basic equation for the Poynting flux associated with the magnetic energy, which can be expressed in terms of the B cross E. E is here again a cross product of the velocity and the magnetic field. The vertical component of this magnetic energy Poynting vector, it is having two terms. So the first term here tells us about so here the subscript Z and H tells about the vertical component and the horizontal component. So the first term is telling us about the dynamics in the vertical direction of the horizontal magnetic field. When I say this, what I actually mean is the flux emergence kind of a scenario. So we have this horizontal magnetic field which is rising from the photosphere, and as it goes up into the solar atmosphere, transversing through different layers, and it can be able to rise and give the kind of the observations of the different structure that we have been observing. However, the second term here, it talks about the horizontal motion associated with the vertical component of the magnetic field. So what that actually means is that we do have the magnetic field lines, and they are being perturbed, and that is actually going to inject the transverse wave energy, what we generally see into the different other layers of the solar atmosphere. So what mechanisms do actually generate these transverse motions are kind of like, we don't know precisely what they are, but that could be a combination of multiple factors. It could be the changes into the internal and the external pressure, both plasma and magnetic linear input points. It could also be associated with the flows which surround the magnetic flux elements. It can also be due to the change into the topology, into the change of this the cross-section area of the magnetic element itself. So, or it could be a combination of all these kind of features, but we are not very much sure. But what we do know is that these kind of processes here at the put point injects these transverse motions, and that what we can be able to expect to see into the different observations. And talking about the observations, we do see these kind of motions kind of very routinely. So here at the bottom, we do have the observations in the G-band taken from the CRISP instrument at the Swedish Solar Telescope. And this is the region where we do have the plasma pressure dominating the magnetic pressure. That means the plasma beta is greater than 1. And you can see these magnetic bright points, which are being shuffling around due to the convective motions in at the granular scales. So these are being regarded as the foot point of the magnetic field lines that we observe higher up into the solar atmosphere. Going up in the chromosphere, where the conditions are even more complicated, the plasma beta varies across the unity, and what it means is that this structure actually goes from the regions where the plasma pressure is dominant to the magnetic pressure dominant regions. And while doing so, these features do show the bulk motions, which are the transverse motions, and kind of everywhere where we see, whether we are looking into the regions with weak magnetic concentrations or the regions with the strong magnetic concentrations, these are kind of ubiquitous in there. Moving up higher into the solar atmosphere in the corona, we do have observations from COMP instrument, and this is the region where the plasma beta is less than 1, which means the magnetic pressure is the dominant. Here, from the COMP observations, we can see that there are cubic motions used, these transverse motions, and the corona is kind of being filled up with these sort of waves. One more thing, what we can be able to see in these observations is that the transverse motions are kind of propagating away. So the transverse oscillations are not only limited to the corona itself, but even goes beyond into the interplanetary media. So here are one of the first observations that were being reported by Mariner 5 at Venus in 1971, and they have found on the y-axis we do have the 3 components of the magnetic field, and on the other axis we do have the components of the velocity field, and and that could be resulting into the kind of the transverse oscillations that we have been observing into the interplanetary region as well. So the kind of the impression what we have been getting is that these are kind of ubiquitous, whether we are looking at the foot points, we are looking into the
sorry to interrupt. Somebody is asking to talk a little slowly.
Okay.
Because of the sound quality.
Closer to me. Where's the mic he's talking about?
So
Okay, I'll just go to the front then. Sorry about that. So then we can kind of like what the impression is that we see these transverse waves which are kind of everywhere in the solar atmosphere. Now, another factor is about like what exactly is these transverse motions that we have been looking at, like whether we are being looking at into only the bulk portions or these are a combination of other wave modes as well. So here we do have, so the general term that we use to describe these motions are the Alfvénic waves. So the Alfvénic term come into the play because these are not having only the transverse motion, but a combination of other motions as well. So the Alfvénic also means that we do have the other kind of the waves, depending upon the phase speeds, whether the fast, slow, or the kind of the Alfvén modes, which are being coupled together because of the inhomogeneous solar atmosphere. However, the different kind of the kinematic modes that we observe, they are also being coupled together. So here we do have an example of a spicule that being observed using the Swedish Solar Telescope in the H-alpha wavelength. And what we have actually done that we kind of like for different heights and over the time, we try to disentangle the different kinematic modes that were being presented into there. So we got the transverse oscillations, we got the cross-section width variation, and also the rotational component. And then we kind of merge all these different kinematic parameters together for the visualization. And then here we can see that these transverse motions are not acting alone, but they are being acting again in combination with the cross-section width variation, and also in combination with the rotational motion, which is which is perceived as the rotational alpha waves or Alfvénic waves. Here in the bottom, we do have these sort of the phase relationship between these motion in both the frequency domain and also in the wave number domain. And if you can see that most of these the phase relation are kind of concentrated near the 0 or the 180 degree plus minus, which gives an impression that all of these motions are intrinsically coupled. So when we have been looking and we are trying to understand the kind of these the motions, the transverse motion, we are actually talking about the bulk transverse motions, and that's where this nomination about the Alfvénic comes into the play. Moving on, here from the theory, what we generally kind of summarize what exactly we know so far about these motion. So there are certain assumptions which will start in the linear MHD regime, that the geometry we are assuming is cylindrical. It's a very simplistic assumption, but still a very robust one, and being able to explain many of the things so far. Second is the long wavelength limit, and by that I mean that the tube radius is a bit smaller as compared to the observed length of the structure itself. Now, we subscribe to these assumptions, then the key property that we get for these motion are that the magnetic tension remains the dominant restoring force. These motions are highly incompressible, nearly dispersionless, and propagates vorticity. So here, for these is the visualization of these circular geometry flux tube motions, and here in the red, you can see that the magnetic field, which is the inside of the flux tube, and the blue, which is a region which is outside. The red and blue here are actually telling about the density changes, which are due to the perturbations associated with the dynamics of the flux tube itself. Now, what we know from the theory is all these different parameters can be related into this very simplistic expression. This is being derived, and I am just presenting the very simplistic version of the expression we can get for the phase velocity. So the phase velocity is basically the sum of the magnetic field inside and the external or the outside the flux tube, and again, which is in the density also we can just see into the inside and the outside. If we take an average of that, then here we get a very simple term which relates the phase speed of these particular waves with the magnetic field and the density itself. And this is the kind of very simple expression becomes the cornerstone of the seismological application of these waves and how we can be able to deduce the different parameters, which are not very easy to get directly from the observation itself. So before going into any of these particular examples, I will be a bit more biased here towards, because I will be presenting most of these outcome from the comp of observations only. So most of us might know that the comp is, and now the upgraded comp is an instrument located in Mauna Loa, Hawaii, and it's a coronagraphic spectropolarimeter that can observe the corona not in one wavelength but in multiple wavelengths. However, what we have been using is mostly the 10747 angstrom wavelength, which is correspond to the RN13 line, and it has a spatial sampling of 4.6. Now the UComp has slightly better of around 3 arcsecond. Cadence is around 30 seconds, and the observational field is at the off limb, which goes from 1.05 to 1.3 solar radii in terms of comp, and 1.03 to around 2 solar radii for the UComp. So in most of the analysis that I want to present is going to be using either the intensity observations, the line of sight Doppler velocity, and maybe for some time the line width observations as well. So the first example, like if you just want to subscribe in terms of the magnetoseismology application that I showed here before, is these particular 3 parameters that we just want to know. The first one is the phase speed, and if we know the density as well, then we can get an estimate of the magnetic field, the plane of sky component of the magnetic field. So the first is an example from the coming from the Scott McIntosh and Steve's paper in 2009, where they actually investigated the data from the comp and tried to get the idea about the propagating phase speed of the waves. So if we do know the structures into the comp, whether it's closed field line, open field line, and we do realize that these transverse waves are being propagating along the magnetic field, then by taking a slit across this particular region and then taking those, stacking those particular pixels over the time in this direction, we can get these time distance map. So the time distance map actually tells us about the inclination of these strands. If you can see, give us an idea about the propagation speed of these waves as well. Now, getting into the Fourier domain, we can disintegrate this time time distance diagram into the Fourier spectra, and that's where we get the inward as well as the outward. So this gives an idea that these waves are not unidirectional but bidirectional. So we do have the outward propagating waves and we do have the inward propagating waves as well. And we can get in some sort of an idea from here as well that the outward propagating waves have slightly more power than the inward propagating waves. However, we can do an inverse FFT and we can get these, but we can sort out these two components as well, and then we can get the phase speed which are being associated with the waves which are being propagating radially outwards or which are being reflected back and coming back to the solar surface. Now, one of the application of this kind of technique is to estimate the flow speed. So using this particular relation, we know that we generally saw that the velocities which are for the outward propagating waves are slightly higher than what we are getting for the inward propagating waves. Now, using the difference, because that could be possibly due to the additional flows that kind of supports the outward propagating waves and they provide an additional thrust. If we can be able to take a difference between the outward and the inward component, we can somehow get an idea about the flow speeds, which is related with the solar wind, the speeds which are originating in the inner corona. So this is something what Richard Morton has done in 2015, and what he has got is, this is the outward propagation map, and this is the inward one. Some of the pixels slightly here has more velocity, so we believe that the phase velocities here were not very accurate. However, if we take a difference of these two maps, we get the flow velocity for the solar wind. And here they have actually compared their estimates from this technique from a 1D dimensional solar wind model coming from Pinto et al. In 2009, and at some of the regions in the limb, it kind of matches fairly well. So this is one of the applications where we can be able to take the solar wind outflow velocity very near where exactly the solar wind is being originated, much before where it could be sampled in situ at 1 AU.
May I ask a question?
Sure.
Are those predominantly open field lines that you're looking at?
Yes. Yeah.
And I have a question. What those negative, the blue things mean? They are inward?
Yeah, so basically, like if you take a difference, then the difference between outward and the inward. So basically, those particular flow velocities are basically we are taking the absolute values of that. But when you take a difference, then they are just taking the sense of the direction. And this is it. Moving on. Now we have the phase velocity. Now we need to know the density parameter. So here is again one of the observations which were being taken by the Richard Morton in his 2015 paper, and we can subscribe to this relationship which comes from the theory. So the amplitude of the wave fluctuation can loosely be related to a constant which and proportional to the phase velocity, frequency, and the magnetic field. Now we know so far that the phase velocity could be related as the magnetic field times the square root of the density. And if we substitute this relationship in here, we can get an expression of the relationship between the Alfvénic, the fluctuation amplitude, as well as the density itself. Now, using this relationship, what they have done is they try to estimate the density, the electron density parameter. Now, here there are a couple of assumptions which are, when it comes down to waves, are being taken into account. The first one, the waves are not doing any sort of damping. And the second one, we are taking an average of the ion as well as the electron densities together. With those particular assumptions, we can get an estimate of the seismological estimate of the density. Here, these black stars correspond to the electron density, which is coming from the iron-13 line ratio, which is the 1074 and 1079 from the COCOMP instrument. And here is a theoretical estimate of the electron density at the off-limb taken from Cranmer and Van Bullion in 2005 paper. So here you can see, to some extent, the seismological, the estimates for the density falls in line with both the theoretical estimate as well as one which are coming from the line ratios from observations as well. Now, once we have the density here, and we know the phase speed, it kind of becomes quite easy to estimate the magnetic field parameter. And that is what they have done here. And here, these stars are basically showing the magnetic field And the dashed line corresponds to the magnetic field, which we can expect from a BFSS model. And from around 0.06 to around 0.16 solar radii at the limb, we can be able to see that there is a fairly good correspondence between the magnetic field and then what we can expect from the BFSS technique. Very recently, Yang et al. Applied this technique to the entire sun. And what they have actually found using the data from the COMP is on the global structure, the seismology technique can replicate some of the observed behavior of the global magnetic field. However, if you look at the smaller scales, then this technique might not be hold true, primarily due to because it's a line of sight summation of all the magnetic field vectors, and if it is somehow being canceled out, or there could be some other estimate problems related with the phase speed estimates. However, this technique is kind of successful and gives us a fairly good idea of what we should be able to expect from the waves. Now, apart from getting the estimation of these physical parameters, waves can also tell us about right.
Call us.
Yeah. So now, apart from having these parameters, we can also think about the kind of the energy that these waves actually carry. So these waves are known to play a kind of a significant role when it comes down to ground heating and also the acceleration of the solar wind. And the few models do relate to the turbulence, do subscribe to this sort of view, which are being into business for quite some time. So the general idea behind these models are that these waves are being originated near the photosphere. They do follow the magnetic field line, and as they do propagate up, they kind of interact with the gradients into the magnetic field as well as the density. And as they do, there could be reflection, and the counter-propagating waves in the nonlinear regime can actually create the turbulence. So if you are looking at a closed field topology structure, let's say the coronal loops, then there could be the counter-propagating waves which are being injected from both of the end of the loop, and that might be interacting with each other and creating the turbulence. However, in the open field lines, there could be these gradients that might be doing some sort of the reflections, and that is actually generating the turbulent cascade. So having known this, here is the phenomenological approximation. So what exactly the phenomenological approximation says? So the equation for the turbulence are kind of very nonlinear because we are actually dealing with the nonlinear terms in here. Z plus and Z minus actually correspond to Alfvénic variables, which show the relationship between the velocity fluctuations and the magnetic field fluctuations. So the phenomenological approximation can actually help to reduce the very complicated nonlinear terms into the one-dimensional terms, and that can actually gives us reduces the entire approximation to this very simple term where the volumetric heating rate is nearly approximated as some sort of constant, which is a dissipation constant, and the ratio, this particular relation where we have the Alfvénic variables and this particular term, which is the correlation length parameter. So before we go to what exactly this correlation length parameter is and what it actually does, we can check like whether this sort of a very simplistic approximation do hold any good. And can we actually use this sort of thing to estimate the wave kind of energy dumping into the solar atmosphere? And it turns out that yes, it does. So here is, I'm referring to a paper from Steve Kramer in 2017. And what they have actually done is simulated fluctuations into the velocity. And here the dashed line is actually talking about what should be without the turbulence, using this phenomenological approximation, and the solid line is actually one which is corresponding to one which includes the turbulent the parameters. And here we can see that it very nicely follows the kind of the approximations for these perpendicular root mean square velocity fluctuations in the photosphere, in the chromosphere, higher up into the corona as well. So at this particular stage, it gives us some sort of a confidence that yes, we can be able to use these very simplistic approximation to estimate the correlation length scales. So the perpendicular correlation length scale in this approximation, in this equation here, is known in the solar wind community for quite some time. So what this particular parameter tells us about is the magnitude of the heating rate as well as the location. So it does not tell us about that how much energy will eventually end up into heating the solar atmosphere, but it can actually tell us about how much energy is basically available. So if we look at a very, So if we look a very standard kind of this the diagram for the Kolmogorov turbulent spectra, then we can see that here this particular region corresponds to the range where we have the energy containing range. These large scale eddies which hold the energy up in here, they eventually decay down into the smaller size eddies, break down into subsequent range, and eventually reaches to the dissipation scale where the actual heating takes place. So what the correlation length scale talks about is this particular range of the size scale of the largest eddies that would be possible at the start of this particular process. So if you're looking at some sort of a hydrodynamic eddy, then we will have this sort of shape, and there's no preferential location where we're going to measure the kind of the length scale for these sort of the turbulent eddies. However, when the magnetic field is there, then the magnetic field kind of stretches these eddy along the direction of the magnetic field itself. So then we have two particular directions, one which is along the magnetic field, which is called the L perpendicular, and the one perpendicular to it, which is called the L bulb here. And what we should be expecting is the perpendicular correlation length scale should be very, very less than as compared to those in the parallel regime. So this particular model has used these particular parameters kind of ad hoc for quite some time. So the numerical models that actually use this sort of phenomenological approximation, they kind of use these particular the magnitude by choice. And by choice, what I mean is what kind of results they actually want to reproduce from the numerical models. So again, if we just subscribe to to use the larger magnitudes, then we can have the greater wave damping. If we use a smaller magnitude of L perpendicular, we have the less wave damping, and so on and so forth. So basically, we don't have a particular idea about so far that what exactly this the magnitude of this L perpendicular parameter should be. So here are an example of few of the models where the L perpendicular was estimated at the photosphere, which are of the scale of the kind of the magnetic flux elements that we observed in there in the intergranular lanes of the size from 0.1 to 1 megameter. We have some examples where it is being used at the photosphere of the granule scale. So the L perpendicular was nearly around 5 megameter. And then we had a few examples that talked about at the base of the corona, which is right above the transition region of the scale size of around 10 to 35 megameter. So we didn't have a particular idea that what exactly this value should be from the observations. And that is what we actually aim to investigate in our research. So here comes how we can be able to estimate the scale of the perpendicular correlation length. So we have the line of sight so in this process we use the line of sight Doppler velocity data, and we subscribe to the view that these Alfvénic wave packets are being traveling along the magnetic field lines. So we select any of the pixel, and corresponding to that particular pixel, we can get the estimation of the coherence in the Fourier domain. So just by going around with this particular reference pixel for a certain region, we can get a kind of a map of the coherence, the mean square coherence values in there. So the mean square coherence values, we have used the threshold of around 0.5. So anything about 0.5 is being taken as kind of where the coherence has some sort of credibility. And below that particular threshold value, we have rejected it. Now in here, you can see that the kind of the coherent islands that we have managed to get have the elliptical or the stretched out kind of a shape, what we were basically expecting for the turbulence eddies in the presence of the magnetic field. Then we can use a 2D Gaussian function to approximate the sigma values for this sort of the eddies, and that is going to generate us the perpendicular coherence estimate as well as the one which is the parallel coherence estimate. And this is the process what we can be able to replicate for the entire sun, for all the pixels which are being available. If we can be able to do that, we can get a map of both the perpendicular coherence as well as the one for the parallel coherence. And here is what it should actually look like. So here we can see for from the measurements, we can actually see that the perpendicular coherence, except for some of the regions around the poles, is fairly kind of homogeneous. So here we have actually the closed field line structures, we got the active regions and the regions with the open field line topology. And here we can see that kind of the estimates for the perpendicular coherence are very, very less as we've been getting for the parallel coherence, which we expect from the theory as well as from the kind of estimation what we've been doing. Now, we repeated this sort of the analysis for a number of the data sets over the course of the solar cycle. And here, most of these sort of data sets have been coming from the COM, except for the last one, which has been coming from the UCOM. So that's where we wanted to see, like, what if we do have a change into the pixel size, the resolution, then whether it will affect the kind of the estimation, what we've been doing for the perpendicular coherence or not. And we've actually found that most of these coherence estimates had the probability density peaks, which are lying somewhere between the 5 and the 10 megameter. And over the kind of this distribution over the sun, we can, as I just showed already before, that here is the active region, the background is the K-core image, and the equatorial coronal hole, as well as the pseudo streamer, which is associated with a closed field line loop structure. And then we can see that there's a fairly homogeneous distribution, which is being lying somewhere between the 10 and the 20 megameter. So this is just the perpendicular coherence, what we actually measure so far, and we can be getting a 1/e estimate of this one just to convert it into the correlation length scale. And when we do it, just by multiplying by √2, we get the estimate somewhere between 7.6 to 9.3 megameter, which actually correspond to the scale of the supergranulation and what we are being getting into the photosphere. Now, I already talked a lot about the magnetoseismological applications of the waves, and using the waves itself, we can be also able to get the perpendicular correlation lengths and how these actually go, what kind of relationship these actually show in together. So here it is the same data set, but we have kind of stretched it into the polar coordinate system. So the X is actually showing the azimuth angles. And here we have the same pseudo streamer and the active region. And here we have got the line of sight magnetic field estimation, the perpendicular correlation length scale, the temperature and the emission measure is actually coming from the DEM estimates, and the density is from the line ratios from the COMP instrument itself. So here it is a very preliminary result, so whatever I'm being presenting should be taken with a pinch of salt. However, we can see that for the active region, in some of the cases, we do have a kind of some sort of correspondence between the line of sight magnetic field, as well as the correlation length scale, the temperature, as well as the elevated density. However, this is an ongoing kind of a project, and we might need to see in a few more cases before we can be able to reach any sort of conclusion from here. Now, moving back, here is the kind of the estimation, what we get from the COMP, which is the first one being taken so close to the sun, and how it compares to the other estimates that were being taken into the interplanetary media. So here we have taken the x-axis is actually talking about the height above the photosphere that you can see. The y is the perpendicular correlation length. We have used two different models as well. The dashed line is actually the model 1, which is coming from Alfvénic in 1986. The solid line is from the Steve Kramer and Van Bullion in 2012. And these crosses and the plots are being coming from the estimates which will be taken into the interplanetary media. So the crosses are at around 1 AU, which are being taken from the WIND and the ACE spacecraft. These plus signs are from the Helios spacecraft as well as the Parker Solar Probe. And as you can see that most of these estimates were done beyond the Alfvénic critical zone, and except for this particular one. So this has been coming from the Spengler et al. In 2005, and where they tried to get the estimation of the coronal magnetic field using the Faraday rotation from the radio observations. And what they've been trying to get was and they found that the coronal magnetic field is kind of smooth up to the scale of around 35 megameter, and that's what they loosely translated into the perpendicular correlation length as well. However, this is the only estimate what we have been able to get so far near the sun, where basically the Alfvénic wave energy is being injected into the solar wind. So the model number 1, which is the dashed line, corresponds to the expansion of the magnetic field, basically. So what it tells us that the perpendicular correlation length should vary inversely with the magnetic field magnitude, or as the magnetic field expands. The idea behind this particular model was that the Alfvénic fluctuations remain confined into the magnetic flux element, and as the magnetic field will expand, the that should actually correspond to the extent for which the wave energy is going to be available for heating or powering the solar wind. However, into the revised model, we had got two terms. So the first one did actually incorporated the linear expansion of the flux tube, where A is basically the area, the cross-section area of the flux tube itself. But the second term had the nonlinear coupling between the fluctuations, the Alfvénic fluctuations, as well as the background flows, which is the solar wind coming from solar wind. However, you can see that the estimates what we were being getting were far higher than we can be expect anything from these two particular models. If we scale down these models, then we can get at the photosphere, the correlation length should be of the scale of around 0.12 megameter, which is the scale of the magnetic flux elements in the intergranular lanes. However, what we have been getting is a granular scale of around 1.5 megameter. So the question is why we get these discrepancies between the models as well as the kind of the observational estimates we have been getting. So one of the reasons could be that these models have assumed the homogeneous conditions. These models were being designed for the open field line structures where the fast solar wind originates out of the sun. So in that particular scenario, if we inject the inhomogeneity from the observations, we do know that the solar corona is highly structured, and that can actually play a very important role when it comes down to the wave physics. So in the earlier models, the waves were not being talking with any of the perpendicular other structures or the waves which are in the nearby flux elements. But in case of the inhomogeneity, that not be the possibility. Moreover, the resonance between the different waves which are being propagating in these substructures can actually concentrate the wave energy. And that particular concentration of the wave energy will happen to the scales which are the scales of the inhomogeneity itself. So we do know that I'm just going to show in the next slide what are those particular scales. And again, one more kind of the problem what we may actually expect is all the models had only one Alfvénic waveboard. I am aware of a very recent one which came from University of Tokyo, I suppose, and they have actually got the transverse motion as well as the longitudinal motion as well. However, here is a simulation result, which is actually showing how the inhomogeneity actually comes into the play. So this has been coming from Norbert Magyar and Tom very recently, where they have actually got these velocity fluctuations, and they try to modulate what happens in the case of inhomogeneity as you go radially away from the sun. And here you can see from one solar radii to 7.5 and the 15, the kind of the wave energy, the fluctuations into the velocity kind of concentrates onto some very smaller scales, and that is what the scales they have actually introduced into their model related to the inhomogeneity itself. So the question now comes in that what are those particular scales of inhomogeneity that we have been talking about? So here is one of the observations that come from Craig DeForest in 2018, and they have taken the observations from stereo spacecraft, and here we do have the kind of the coronographic images which is being straightened out in the polar coordinates. So here they have kind of applied some filtering, and we can see these small patches, and these patches were in the intensity corresponding to the density inhomogeneity. So the size of these patches, which are around 8 to 12 solar radii, were of the scale of the 20 megameter. And what we are being observing near the sun, which is between 1 to solar radii, is basically around the scale of the 10 megameter. So if you're going to scale down these inhomogeneity factor to the region where we have taken our observations, you may find a very strong correspondence between the density inhomogeneity itself as well as the kind of the estimates, the elevated estimates what we have been getting. But the kind of the inhomogeneity and doesn't even stay in the near sun environment. If we even go out, because like what we have seen compared with the kind of estimates at the 1 AU, and in between that, we did had most of these observations were taken before the Alfvénic critical zone, and we are the only ones which had the estimations before the Alfvénic critical zone in here near the sun. So what exactly the role the Alfvénic critical zone will play into these sort of behavior? So here is a kind of a simulation results coming from Rohit Chivar, which published in 2022, and what they actually found that the Alfvénic critical zone is very patchy. Now, what does it mean? What is going to do if the Alfvénic critical zone is patchy in here? So the black curves here are actually talking about the surface, which is coming from the averaging the fields. The red curves, what we're seeing in here, are the start and the end location for the extended region where the Alfvénic critical zone should be. Now, this patchy behavior is where the solar wind is actually changing its character from sub-Alfvénic to the super Alfvénic. Now, if you assume that there is a kind of a solar wind, a kind of a propagating Alfvénic wave packet which is coming out from the sun and going moving in the radial directions away from the sun, it will encounter these small patches. Now, at these particular small patches, as I said before, that whenever these waves, after propagating waves, experience some sort of gradient into the magnetic field or in the gradients into the density, they can actually have some sort of the partial reflections. Now, imagine if the wave is being propagating outwards, it encountered these patches, it will have these reflections that will generate the inward propagating waves as well. Now, due to these particular continuous kind of the patchy behavior, the inward propagating waves may again couple up with the outer propagating waves into some other region which is coming from the sun on the back and create an elevated amplitude of the Alfvénic wave fluctuations. Now, that particular elevated or the higher up the amplitude of the waves will generate into the stronger turbulence behavior. So here we do have a very high the regions with the turbulence, and again we do have the background solar wind, which is always being coming into the outward direction. And again, at this particular stage, if you subscribe to the model number 2 that I shown before, when we do have the coupling between the fluctuations and the background flow, then this sort of the behavior is going to elevate even into the further. So whatever the kind of these perpendicular correlations where the wave energy is going to get dumped into the nearby atmosphere is going to be very different from what we have been getting from the simplistic models and again from the approximations that we have been getting here so far. So we don't know precisely what happens into this particular region, but this is more like a speculation. What we believe on the future missions we can be able to detect. But for the moment, what we have got is this sort of our estimate, and what we will be looking into the future is maybe getting more near to the sun, into the chromosphere, and try to see where we do actually fit into this entire regime. So here I can give a summary of my talk in here. So Alfvénic waves do have the capability of acting as the diagnostics for density and for the magnetic field. It can also provide the estimate of how much energy could be dumped into the solar atmosphere that can eventually power the solar wind. It can be also heat at the solar atmosphere. From our observational results, we have found that between 1 to 2 solar radii, we have got into the range of the super granulation scales. Inhomogeneity is a factor that being not being taken into account into most of the modeling so far, and may play a very critical role when it comes down to the heating as well as the powering solar wind kind of conditions. So these kind of have strong implications for turbulent heating scenarios, for the shock heating scenarios. And yes, again, our estimates come from observations, so that provide a key constraint for the different Alfvénic wave turbulence models. So in case you're being interested, we have got the paper out, and you're very free to see and read. Thank you.
So, questions? Anyone from the hall or online? Please unmute and ask your question.
What's an eddy for you? Like, how would you define an eddy?
Okay, so what we believe is like when the waves are having a nonlinear interaction, that will actually give rise to some sort of instabilities. So in the very generalistic kind of very basic idea is about this Kelvin-Helmholtz kind of the interaction.
Mm-hmm.
You do have the two streams which are in opposite direction. When they kind of interact, in case of the waves, if there's a linear interaction, they will kind of cancel each other or kind of superimpose upon each other, where you're going to see these elevated crest and flows. However, in the nonlinear regime, they are kind of create these sort of the instabilities in that particular location. And the size of that instability is going to be what we believe is the size of the eddy itself.
So this in my head is really hard to reconcile your finding of like 7 to 10 megameter structures when we have observations from high sea which are like 20 times better resolution than this, and we don't see there any sort of instability that's ubiquitous throughout the corona.
Yeah.
So it's kind of hard for me to understand how you reconcile the two when you're kind of finding something that's on the order of the diffraction unit of the instrument.
Yeah. So the reason why we don't see many of these eddies is because we are looking into the intensity observations. And I believe the high CE has also taken observations with intensity.
Mhm.
And with the intensity, that will be very hard to see because these are the eddies which are being coming into the magnetic field is the dominant force. And we can't be able to see any of the magnetic field which is being doing any of these magnetic role. So that could be the one of the reason. The second one is that here we are getting the largest scale, which is being depending upon the kind of the data and the resolution we have. However, there is no way we can actually subtract that there's only one kind of the scale of the perpendicular correlation length, and there could be more scales which might be in there. So depending upon the resolution of the instrument that you might be having, you might be able to see these different scales of the correlation length or the different scales of the eddies into the solar atmosphere. However, it will be very difficult even to get any of the wave estimates using only the intensity as estimates, because the intensities will only highlight the kind of the field lines that's in the ground loops. And when you actually observe it, like the kind of the simulation results, what we recently came out where they have shown these loops may not be actual field lines, but kind of a superimposition of different density elements, which gives a perception of what we were looking at as loops. So. Sure.
So what observations would you need for that? I mean, would you want to be observing a time-varying magnetic field measurement? And if so, what might that look like?
We are not sure because we haven't got any of those particular observations so far, because then we need a kind of temporal evolution of the magnetic field and to what particular scale these magnetic fields are going to be in a coherence. So in the coherence, we can be able to see that, okay, well, this is the scale where the magnetic field is kind of being expanded out. That's something what the Spengler law in 2005 actually did. However, when it comes down to these instabilities that will be near the magnetic field, and the instabilities are going to create these sort of the turbulent behavior, and what we expect is that to what particular scale this turbulent behavior is growing. That's what we actually try to measure in here. So what we do know at the moment is like from the comp observation is that we have got waves and the waves are in sync at this particular scales. So if the waves are in sync in this particular location, then the largest eddy it can generate would be into this particular size as well. And if you assume that is the size of the largest eddy, which will eventually break down into the smaller eddies, depending upon the observations you're taking, then eventually. But however, when you want to see the smallest kind of eddies at the dissipation range, we won't be able to see at all, because they will be at the scale of a few centimeters. And that might not be even possible from the highest resolution instruments. Yeah.
So would something like high C type resolution, but with Doppler shift?
Yeah.
Would that answer these questions?
Yeah.
Okay.
It could do.
And is cryonurse on DKIST approaching that?
Well, it's going to be better than comp, I think, by a factor of 3 or 4. So
Okay, so not quite high C, but
Wasn't high C lower than the chromosphere?
right. Yeah. High C was just a.
But you need that resolution in the corona, you're saying?
Yeah.
Okay.
well, I still was in the corona.
It was on disk.
It was on
Yeah.
171 and 193.
Oh, okay.
Yeah.
On this. Gotcha.
But again, with like very high resolution observations, you will see the different scales of these coherent eddies, what we say. But again, like what I'm saying again is like we should expect a large variation into the size. And so what we are just talking about is the largest scale that you are going to expect into the solar atmosphere. But again, there is no other reason why if the higher resolution, may be able to detect some of the scales which are a bit more smaller. So yeah, that could be the case. Sure.
Johan?
So does the line of sight integration effect have anything influencing your estimate of this cross-particular correlation?
Yes. So the line of sight integration is going to take account of all the structures which are behind the kind of the all observations. And what we expect is lowering down into the wave amplitude. However, what we are doing in here is not playing around with the amplitude of those waves, but we are just trying to see how many of those particular waves in that particular in the pixel are in coherence. So you do have the waves which are basically having some sort of amplitude, but what we just want to see is how many waves are having the similar sort of a pattern over the course of the time. So we are more interested into the pattern rather than the amplitude wave itself.
Oh, that's interesting because that's something that we can now probably start to test because for the punch mission, we're building up these huge cubes of turbulent simulation data, stacking them and putting them at different radii and doing the line of sight intervals through them. And I'm wondering if we could use that to sort of reproduce those probability distributions of correlation lengths.
I mean, so.
Might already exist.
Yeah.
And most of the field lines in the field of view course are closed. And I think you said you were going to identify, but try to isolate the open fields and look for a difference in
Yes.
the correlation line.
Yes. So what we've been trying to do at the moment is to find like if we can be able to take different regions in our estimation. So what we can actually do for what our codes can actually do is they can actually estimate for all the regions. And it is basically independent of each other because for every reference pixel, it is just taking the surrounding pixels. So it is going to a certain threshold of like a box of around 64 by 64. And when the kind of this coherence kind of dies away, it kind of stops, and then it will go to the next reference pixel, and so on and so forth. So yeah, so again, what we are planning to do is to get for different data sets, what we got is like we can isolate the active regions and the open field line regions, let's say here, which is the equatorial coronal holes, and again, the closed field line structures and trying to see. So a generalistic, what we've been getting so far is that most of these perpendicular coherence lies between the 5 and the 10. So any kind of the difference shouldn't be that big. Like that is the kind of impression what we're getting. However, again, of course, there should be some sort of role of topology which will play and generate the kind of the different sort of the turbulence that could be able to trigger in.
Yeah, I'm wondering, is it worth maybe considering a 789, the iron 10 line that UComp observes doesn't have as good of a signal as 1074, but it's more appropriate temperature maybe for the open fields. And could we start running maybe some wave programs in the 789? And then like same day, you run it with waves in 1074 and waves in 1079, just to get a feel.
Sure.
That would be different.
Interesting.
Yeah. I have a dumb question about the solar wind. Ask you or Steve. How do you have all these different magnetic structures affecting over the satellite, and it's measuring these lengths in the solar wind? It's just some time average to get those perpendicular correlation rates in the wind. Is that how that?
Yeah, I mean, there's single spacecraft methods of doing that where they just use the time, forward or backward to figure out, and then map it to length scales just by the speed of the solar wind. But some of those data points I think were gotten from like Cluster and MMS and other multi-spacecraft things where they can disambiguate the space and the time.
Yeah. So here, like the ones in the crosses, they have actually taken the data from two spacecrafts. So one is the ACE and another one is WIND.
Yeah,
Okay.
Ace and wind.
Yeah, so they're using because both of the instruments can actually measure the magnetic field vectors as well as velocity vectors, and they're using that data
Okay.
to mostly find the correlation landscapes in there.
Parker Solar Probe is on its own though. I think that's less certain.
Yeah.
Any other question from online or from the hall? If no, let's thank our speaker again for a very nice talk.